All right, so today we're going to be starting in on Chapter 18. Kind of good news, bad news. Chapter 18 very much so picks off where Chapter 17 left off. So, the bad news is you can't forget everything that we did in Chapter 17. The good news is a lot of those skills we're going to practice over and over again. So that'll be good for the exam, okay? Chapter 18 is sort of all about aqueous ionic solutions, and there's kind of a few little disjoint topics that we're going to cover for this chapter. The first one that we're going to focus on here today is a buffer solution. Okay, so a buffer solution is a mixture of weak acid and its conjugate base, or a weak base and its conjugate acid. All right, so I take some weak acid, I also take some of its conjugate base, and I mix these two together to create a buffered solution. All right, so buffered solutions are used very commonly, especially in biochemistry. I worked in a wet lab for 5 years in biochemistry. Every single experiment I ever did involved a buffered solution. It's very, very important, especially in biochemistry, because what a buffered solution does is a buffer is resistant to changes in pH. Resistant. All right, so what the buffer's doing is keeping the pH within this certain narrow range. Our bodies employ buffer systems all the time because all of our different tissues like to be at slightly different pHs. ATP, for example, when it's created, is a very acidic compound. We don't, of course our body needs this ATP to run. Well, we don't want it changing the pH of our cells when it's being created. So our cells have this buffer system in place that will resist any changes to pH. Okay, that's what a buffer is doing for us. All right. And the last thing we want to sort of make note about a buffer is all buffers have an effective buffering range. And that is when the pH is equal to the pKa of that acid plus or minus 1. Okay, so we have this table of our weak acids, and they all have these Ka values. And we talked about how we can find the pKa by taking the negative log. Why would we even bother to go through that step? It turns out to be a very convenient quantity, especially when you're talking about buffered solutions, because again, a buffer is only good when the pH is within plus or minus 1 unit of that pKa value. Okay, and that means it's most effective. Again, by effective, I mean at resisting changes to pH, when the pH of the solution is equal to that pKa. All right, that's when a buffer is going to be most effective at resisting any sort of changes to pH. All right, now obviously the name of the game here is we're going to start doing some quantitative stuff, right? Incorporating what we know about pH into these buffered solutions. But just to sort of, again, background, explain what a buffered solution is, I take some weak acid, I take some of its conjugate base, I mix them together, I get what we call a buffered solution. This buffered solution, its whole goal in life is that it's resistant to changes in pH, right? So if I add some acid to it, the pH isn't going to change very much at all. All right, again, resistant to changes in pH. And again, it's only good within this effective buffer range when the pH is plus or minus 1 unit from its pKa of that weak acid. All right, so let's do some quantitative stuff here. So first of all, let's go to our table. We're going to get a weak acid here. We're going to be talking about a solution of formic acid. So we're going to need this pKa value. All right, and so if my weak acid is this formic acid, HCHO2, everybody take a second and give me the formula for its conjugate base. This is something that we should be able to do based on chapter 17 knowledge. Right? Do acids donate protons or accept protons? Donate, so I'm going to get rid of one, right? I'm going to go down my number of hydrogens, and since I'm losing that positive ion, I'm got to give it that charge of -1, right? Go down in number of hydrogens, down in charge. All right. And this conjugate base, is it weak, strong, or neutral? Weak. All right, that's the whole shtick of a buffer. It's a mixture of a weak acid and a weak base. Okay? Again, it's its conjugate base of our weak acid. So, we're going to prepare a solution. Where the concentration of our formic acid is 0.75 molar, and the concentration of its conjugate base, 0.98 molar. What is the pH? All right. So we could actually do an ice table, sort of do this the long way here, but there's this very simple equation that we're going to be able to use, what's called the Henderson-Hasselbalch equation. Okay. The one thing about the Henderson-Hasselbalch equation that we really have to be careful of is this works only with buffered solutions. If we're talking about a buffer, great. We can use the Henderson-Hasselbalch equation. But we just got to be careful to not go willy-nilly using this equation, all right? This tells us that the pH is equal to the pKa of my weak acid plus the log of the concentration of the base divided by the concentration of the acid. All right, so again, buffered solution is a mixture of an acid and its conjugate base. I got to know those two concentrations. If I know those concentrations as well as my pKa of my Ka, I can find my pKa of my acid that I'm talking about, then I can always figure out the pH of that buffered solution. Okay? So, using this equation here, we looked up formic acid. We said that the Ka was the 1.8 times 10 to the -4. So in order to get the pKa, I'm going to take the negative log of 1.8 times 10 to the -4. And then I need to add the log of these ratio of concentrations. The base, my conjugate base, was the 0.98 molar. And the acid component, my formic acid, was the 0.75 molar. All right, so then let's calculate the pH. All right, plug that all in. I get that my pH is 3.86. We're not going to worry about sig figs with these here. All right, so we'll just say 2 decimal places. All right, but that's how I can use my Henderson-Hasselbalch equation to pretty easily, without having to go through the steps of the ICE table, figure out what the pH of my solution is for my buffer. All right, I got to know the concentration of my acid and its conjugate base, as well as the pKa, which I can look up from my table. All right, but that's how I can figure out my pH of a buffered solution. All right, now we said our buffer is most effective when the pH equals the pKa. What is that ratio of conjugate base to acid when it's most effective? Right? I sort of told you a buffer is best at resisting changes to pH when the pH of that solution is exactly equal to the pKa. How do I prepare a buffer where the pH is the pKa? Right? What is it going to be, that ratio of acid to base that I'm going to need to use? Or I guess base to acid. All right, so if the pH is equal to the pKa, how can I find what that pH would be? How do we find a pKa? Negative log of the Ka. All right, so let's figure out what pH that would be. All right, so that would be 3.74 equals the pKa, which is that 3.74 plus the log of base over acid. All right, concentration of base over my concentration of acid. What am I going to do next? I'm going to solve, right? How am I going to solve? What am I solving for? This is my variable here. I need to get that all by itself. So what am I going to do first? I'm going to move that 3.74 over. Since it's addition, I got to subtract it from both sides. I need to get myself some more room. So that means that the log of this ratio is equal to 0. How do we do the inverse of a log? Does anybody remember? 10 to the, right? So we're going to raise both sides, 10 to the power of both sides. So that means my conjugate base over my acid, my ratio, is equal to 10 to the 0. And what happens when I raise something to the power of 0? I always get 1. Right? So that means that if my ratio of acid to base is equal to 1, that's the same thing as saying that those concentrations are the same. Right? So what we just established here is that the buffer is most effective when the concentration of base, conjugate base, is equal to the concentration of acid. right? This means concentration of base is equal to acid. That's when the pH will equal the pKa. So if I start my buffer with an equal ratio of acid to base, that's when it's going to be the most effective. All right, so let's take a look at this reaction real quick. If I place my formic acid into solution, all right, again, we say that this buffer is resistant to pH changes. So let's say that I prepared a buffer solution, and now I'm going to add some strong acid. Which direction? Okay, so let's say that I prepare this buffer solution, and now I'm going to take my buffered solution and I'm going to add in some strong acid to it. If this is at equilibrium and then I add in some strong acid, which way is that going to shift this reaction? In favor of the products or in favor of the reactants? Left or right? Let's see. Who thinks it's to the right? Who thinks it's to the left? Who's got no idea? All right, so remember, when I say adding strong acid, which one of these components am I adding? Right? Strong acid is really just code for hydronium ions, right? Because every bit of strong acid that we add, we will add it, it will dissociate completely, and so we'll be adding in those hydronium ions. So if this concentration is increasing, thinking back to what we learned about equilibrium with Le Chatelier's principle, that will push that reaction in this direction, back in favor of my reactants. Okay, so that Le Chatelier's principle essentially just is illustrating how a buffer is working, because it's this dynamic equilibrium that can shift in one direction or the other, right? And so by adding some strong acid, what I'm really going to do is then shift this equilibrium back in favor of the acid portion. All right, so then let's do these sort of problems quantitatively here. All right, let's see what happens to the pH quantitatively when we start adding some acid in there. So again, let's go to our constants page. Let's grab an acid to make a buffer with. Let's do this one here. Great. Sounds good. All right, so if my weak acid is this HCrO4 minus 1, everybody take a second and give me the formula for the conjugate base. right, so I'm going to go down in my number of hydrogens. And what's my charge going to be? -2. I got to go down in charge as well. All right, so now we're going to make it a little harder, a little bit more practically speaking. If you were in the lab and you had these two solutions, a solution of weak acid and its conjugate base, you mix them together, you're going to have to figure out what that concentration is, right? Because when I mix them, I'm going to be changing the volume of my solution. All right, so now we got to go rewind back to what we learned about solutions. Okay, so first we got to determine the concentration of our weak acid. Okay. And what's the definition of molarity? Moles over liters. So I need moles of my acid over liters of solution. All right, what's my liters of solution that I've just created, all right? By that I mean the total volume that I have now. And right, so how do we get that? We combined our 1.5 liters with our 1.2 liters, right? So now we have a total volume of 2.7 liters. All right, now I still need my moles of weak acid here. What I'm given is a volume and a concentration. If I take that volume, 1.5 liters, and I multiply that by my molarity, right? This is saying there are 1.2 moles of HCrO4 in 1 liter of solution. So if I have 1.5 liters, I'm going to multiply those together, right? Again, going back to what we learned at the very beginning of the semester talking about solutions, this would give me 1.8 moles of HCrO4 minus. All right, so 1.8 divided by my 2.7. My concentration of my weak acid is 2/3, 0.666. Well, we can just do this. 0.6 continued. All right, so given that we just sort of did here, everybody take a second and tell me what the concentration of my conjugate base is. All right, so again, my definition of molarity is moles per liter. In this case, it's the moles of conjugate base in liters of solution. That volume, that total volume is going to be the same, right, because I've combined these two solutions together. Now I just got to figure out how many moles of my chromate ion I have. Whoops, -2. So again, I'm going to use the fact that volume times concentration will give me moles so then I can plug that back in. All right, and that gives me a concentration of my conjugate base of 0.53 continued molar. Jeez Louise. Okay. So hopefully, hopefully looking at it unit-wise works out, but I will just say we're going to play this trick over and over and over again in this chapter. So maybe we just want to have in our notes somewhere that volume times molarity equals moles. Right? We're going to have to play that game over and over and over again in this chapter. And again, you can sort of do it by setting it up and looking at the units, but again, maybe we just want to have in our notes somewhere so it's extra special clear that if we take our volume and multiply it by our concentration, we'll be left with moles of whatever solute we have. All right, so now everybody take note of this Ka value right here, because now you're going to use the Henderson-Hasselbalch equation and you're going to tell me what the pH of this solution is that we just created. Right, we took these two solutions, we mixed them together to make a buffer. What's the pH of that buffer that we just created? All right, Henderson-Hasselbalch, I'm assuming you guys have it in your notes since we did it earlier. It is on your constants page, all right? So that's not a formula that you're expected to have memorized. Again, remember to take a look at our constants page for each chapter so you get a sense of what it is that you're sort of going to be given on an exam. But you will be given this equation. All right, so then I'm going to take the negative log of that Ka value. I'm going to add the log of those concentrations I just calculated. My base was that 0.53 continued. My acid was that 0.6 continued. All right, and so my pH of this solution, well, that's fine. 6.43. We'll just say 2 decimal places. All right, and again, why can we use our Henderson-Hasselbalch equation? Because we're talking about a buffered solution. All right, so now we're going to take this solution. Quantitatively, we're going to figure out what happens when we add in some strong acid, right? Normally, strong acid will change the pH very quickly because it dissociates 100%. But what we're going to see is with our buffered solution, it's going to resist that pH change. It's not that it's not going to go up at all. It's just going to go up very little compared to what it would be if it was a solution of pure water. All right? Oh, I'm sorry, we're adding acid, it's going to go down. My bad. Right? pH will go down when we add our acid. It's just not going to go down as much as if we had a solution of just water, an unbuffered solution. All right, so now we can ask ourselves something along the lines of, all right. So in order to make this one a little easier to start out with, we're going to just say, rather than saying a specific amount of acid was added, we're just going to say that we've added enough that the concentration of our conjugate base goes down by 0.05 molar, right? The acid, as we said before, our acid that's going to be added is going to react with our conjugate base and push the reaction back in this direction. Right? So by adding acid, I'm going to decrease my concentration of conjugate base because that's what it's going to be reacting with. All right, so now we're going to set up an ice table. Okay, we're again going to start with our balanced chemical equation. All right. Look at our ice table. I can go ahead and ignore water because I don't really care about its concentration. It doesn't change. All right, so my initial concentration of my acid is that 0.6 continued molar. Our original concentration of our base was that 0.53 continued. All right, and then I'm telling you that we're going to be adding a concentration of this acid of 0.05. All right, now this next step, usually we put variables here, right? And we're trying to figure out how much it changes. That's not going to be the case when we're doing these buffered solutions, okay? Because we're going to be able to use a principle that we relied on before with regard to strong acids or strong bases. And that is for strong acids, all of that hydronium ion is going to react. right? So for my change, I know exactly what's going to happen here. All of this 0.05 of my strong acid is going to react with my conjugate base. All right, let's think about it here. This 0.53, should this number be going up or down? Down, right? That's what's reacting. It's kind of weird because I've written my balanced chemical equation this way, but we're actually looking at it going this way here, right? Because again, by adding the concentration of acid, I've shifted it towards the product or towards the reactant side. So minus 0.05. And then is this number going to change, this 0.6? Why is that going to change? It's going to increase because that's what I'm creating when I react my conjugate base with the acid, right? So this number is going to go up. All right, so again, all of that acid has reacted, so that's going to be 0. And now I can figure out my new concentrations of my acid and conjugate base. Becomes 0.716 continued. What's up? So I subtracted it from my reactant, my product side, and I added it to my reactant side. Because again, by adding this H3O here, I'm shifting my reaction this way. It's actually going to react with this to create more of this, right? So by adding it in there, it's going to decrease this concentration because it's going to react with it, and it's going to be creating more of my acid. So that's why that concentration increases. All right, so by adding acid, it reacts with the conjugate base to make more of that weak acid that we had in our buffered solution. What's up? So I told you that you were going to add hydronium, right? So again, by adding this hydronium, it's going to react with this to push the reaction in this direction, because that's what happens. If we add product, it's going to shift the reaction back in favor of the reactants. All right, so then I can say, okay, what is the pH of this solution, and what are you going to do? Henderson-Hasselbalch, right? So again, you're going to use that Ka value that we looked up and figure out what the pH of our new solution is. What's up? I took my initial concentration, which was 0.6 continued, like so 0.666666666, and then I added the 0.05 to it. Right? The little bar is like the calculator spits out a repeating number forever. So that's what that little bar is for. Indicates that it's repeating forever. Yep. Again, I added 0.6 continued with 0.05. Yep, except for this time I was subtracting it, right? Because it was reacting from there. All right, so to finish this off, 3.8? No, 3 times 10 to the negative 7. All right, so that I get the pH of my new solution that I have after adding that acid is 6.35. What was the pH of my buffer before I added the acid to it? 6.43, right? That's what we calculated originally. I added acid, it certainly went down, right? But if I had added this acid to just regular old water, for example, my pH would be 1.3. Right? If I took pure water, pH of 7, and I added that same amount of acid to it, all of a sudden my pH is going to be 1.3. Right? It's going to drop significantly. So we can see that by having this buffer present, my pH still changed. It's not that the pH doesn't change at all. It's just resistant to change. It decreased by far less than it would if I had started out with just pure water all by itself. Right? That's what my buffer is doing for me. All right, so let's do another one of these from scratch here. All right, I'm going to create a buffer of hydrofluoric acid by taking some hydrofluoric acid and its conjugate base, the fluoride ion. I'm going to mix them together until my concentration of HF is 1.35 and the concentration of fluoride is 1.07. If I'm asking for the pH of this buffered solution, I'm going to use what? Henderson-Hasselbalch. All right, and what am I going to need to look up? That Ka value. So everybody take a second. Find our acid on this chart here so you know what Ka value to use. Hydrofluoric acid. Let's just do a OH minus. All right, so first of all, my pH is the negative log of that 6.8 times 10 to the negative 4 plus the log of my base concentration. Which one's my base? The fluoride ion. All right, so now we're going to think about it a little bit differently. Now I'm going to add, instead of adding acid, I'm going to add some base until the concentration of hydroxide is 0.25 molar. Okay, so again, we're going to need to do an ice table, but we want a balanced chemical equation. My hydroxide is going to react with which of these two species? HF or F minus? HF, right? The one with that donatable proton. So here's my acid-base reaction. Everybody take a second to predict the products of this reaction. Right, this will create more of that fluoride ion, as well as, what's my other product? Water. All right, so then y'all are going to build me an ice table. Oh, JK, we're going to do it real quick because we are about to run out of time. Again, I'm going to use my initial concentration of my acid and base, my 1.35 for my acid and the 1.07 for the conjugate base. And again, I've created this solution where now I have this 0.25 moles of hydroxide. How much of that 0.25 moles of hydroxide are going to react? All of it, right? So that's the shtick here. You either add strong acid and all of it reacts, or you add strong base and all of it reacts, right? So this is going to decrease by that 0.25. What's going to happen to the concentration of HF? Is it going to go up or down? It's going to go down as it reacts with that hydroxide. And since it's 1-to-1, it will go down by that same amount. And then what happens to the concentration of fluoride? Goes up. Right? I create more fluoride by adding that base. And if I want to find the pH, I'm just going to turn around and plug this right back into our Henderson-Hasselbalch equation, just with my updated concentrations of my conjugate acid and base. Right? So now it's not the 1.35, but rather the 1.10 and the 1.32. All right, so you guys can sort of do this one on your own, but just to make sure that we're getting the right answer here, should get 3.25. All right, so we'll pick up here next time. Yep.